Okay. So welcome everyone to the third day of this virtual summer school. Hope you've enjoyed it and learned a lot so far. Today, we will have two tutorial presentations, both about the butler, which you've heard a little bit about prior to now, but you're going to get a lot of detail about the butler. Now, then we'll do a break and do, as we've been doing each other day, set aside the last bit of time for working together in breakout rooms. So, let's see. Here we are. So I will be presenting the first part, the introduction to the butler, and Douglas will be presenting the intermediate queries with the butler. I wanted to, since this came up last night, I wanted to add a comment or comment briefly on something that came up that we forgot to show you guys earlier. So if you want to, for example, if you want to clone a GitHub repository to your space in the RSP, for example, the delegate contribution notebooks, which we've been referring to frequently, the way to do that is to actually, the easiest way to do it is you can actually access a terminal from within your RSP instance. So the way to do this, recall that when you first log in, you often see this launcher page. And so, the top thing you see here, if you click this button, it launches a Jupyter notebook with the LSST science pipelines. But if you look at the options down at the bottom in the other section, you can see that there's an option to open a terminal. And this can be used, you can do things, that you can typically do in a terminal. You can actually run the LSST science pipelines from this terminal. And what I wanted to show you specifically, the easiest way to get, for example, the delegate contribution notebooks or some other repository into your space is to go to that repository, grab when the green button that says code here, when you click that, it opens this menu and you can copy the path to this repository, and then go back here and I'll put it in I'll make a temporary directory to put it in. And then, here, I'll make it bigger so you can see too. And then you can just git clone that repository, putting in the link that you just copied from the other page. That will bring over everything from that repository. So you'll see if I change to that directory, you'll see that now I have a whole bunch of notebooks, each in their own subdirectory. So I just wanted to show you that because it came up yesterday a few times that people weren't aware that this was a way to work in the RSP. So yeah, remember the terminals there. You can also use this as a place if you want to pip install some software that you want to use. That's a place that you can do that. Okay, but for now, you've been promised an hour about the butler. So let's start with an intro to the butler, and then Douglas will give you some intermediate data access with the butler. So in this case, we're just going to do very simple things to query and retrieve images and catalogs from the butler. And there are links here that I won't go through all of this information, but you've seen us do it a couple of times where we've created an instance of the butler and used it to retrieve an image, for example, but we'll go through that in a little more detail so you can understand that, understand what it all means. But the butler is basically it's an interface, basically to abstract away having to know where files live, how they're all related to each other. The butler knows about all of that and can basically be used to find things based on their properties. And so it's meant that you shouldn't ever need to go and actually find a path to a file. You'll just find the data ID in the butler and then tell the butler, go get me that file or the contents of that file. So you've seen examples of it, and we'll show you a lot more detail about how that works. So first we just import some basic packages, and most importantly here, the DAF butler package. DAF, that DAF, by the way, stands for Data Abstraction Framework, I think. Don't quote me on that. Okay, so to create an instance of the butler, again, as you've seen us do a couple of times, the two things that you need is you need the configuration, which basically the configuration is what tells it where to find the definition of this repository. It'll point it to a database that has all the information about the repository. That database lives in, the definition of that database lives in these files called butler.yaml in the top level of the repository, the butler repository. And then the second thing you need is a set of collections. It can be a set, it can be multiple. For the DP0.2, we'll almost always just be using this one collection. Oh, thanks for the correction, Aaron. I couldn't remember if it was abstraction or access. But a collection is basically like, I know what it says. It's a group of related data sets. So for example, if you're processing a set of data, starting from raw images all the way through to coads, those are all interrelated, so they will all be contained within a collection. And so in this case, we're looking at the config is just this alias that points us to the data preview 0.2, and then the collection is this particular run. This just contains all of the processing from when this data preview 0.2 was processed. So all you need then to instantiate the butler is you say daf butler.butler, and you give it config and the list of collections. If you want to learn a whole lot more about the butler, you can uncomment this and see lots of information as usual. So that is some reading for later, light reading, I'm sure. Okay, so you can use the butler to access images. You've seen us do that a few times. There are three that we're going to look at here: the CalExp, or the process visit image, a difference image, and a deep coad image. We'll show you how to access each of those types. So to do this, you have to tell the butler what data you want. So you need to tell it the data set type. So for example, the deep coad or CalExp, or an object table containing a table of data, catalog data. And then you define that by creating this thing that looks like a dictionary that specifies a particular data set. So the CalExp images, the processed visit images, these are basically the single visit that has been, minimally processed to correct out like instrument signatures and such. So these are the CalExp. For these, all you need to uniquely specify a CalExp is a visit and a detector. So the visit number tells you exactly that exposure that was taken in this case. And then the detector can be one of the 189 detectors in the camera. And then all you need to do is say butler.get that data set type and the data ID that uniquely specifies that. And now we should have a Calyx image in memory. If you want to see all of the possible dimensions that could be given in this data ID, there are more here, but some of them are not required. So this is the minimum required set in this case. So this butler.registry.get dataset type tells you for this particular data set type what its dimensions are and what type of object it is. So this is just, this exposure F is sort of just an object that contains the image, its variance plane, its mask plane, its point spread function, its WCS, various things like that. Okay, so now we just do a quick using AFW display, which you've also seen a couple of times. Let's just display that calyx.image. Hooray, it looks like a scientific image. We have retrieved an image, excellent. Throughout this notebook, we're going to do this cleanup where we use this GC, it's a garbage collection routine just to free up the memory so that when we grab another image, we're not overloading our pod. So this is just deleting that and cleaning up the garbage. So another example of things that you'll see or that you might want to look at are difference images. So these, one of the difference image exposures or data set types is known as the good seeing difference exposure. It's kind of a mouthful, but this is where you have a template image of the same region of sky and you subtract it off of your Calyx, process visit image. And any residuals should be things that have changed in time. And so again, because this is created from a single visit, all you need to uniquely specify it is the visit and detector, and then you give the data set type. And so let's take a look. Now, because it's a difference image, hopefully almost all the pixels are zeros. And indeed, it's a mostly blank image. And what you should see is either things that didn't subtract very well or things that may have changed between the template and the visit. Okay, so that is one other kind of image. And then finally, there are the coad images, which are taking all of the overlapping Calyx process visit images at a particular place in the sky and co-adding them, just essentially summing them together. These then, because you need to define sort of a sky map that contains these, and so these are divided into what we call tracts, which are kind of larger regions on the sky, essentially of a size that they could share the same WCS. And then they're subdivided into patches, which are 4K by 4K pixel images, essentially, so they easily fit into memory on a typical computer. And that patch size is also very similar to single detector from a Calyx image. So for these, you need to specify the tract and the patch to uniquely specify a deep coad. And you also need to specify the band because you can have a coad in each band separately. So now we need to specify that we want the I-band filter. for this deep coad. And now you can see this is a much deeper image with a whole lot of good stuff going on. Lots of stars, lots of galaxies in a big galaxy cluster. Okay, so those are 3 image types. You can also access the data tables. As we have mentioned, the preferred method of accessing catalog data is to actually use the TAP service, the Table Access Protocol. But you can get the catalogs from the butler. The catalogs typically, corresponding to a CalX image, there is a catalog known as source SRC that has a one-to-one correspondence for the same data ID. There's a CalX and a source catalog. For the deep coads, those will be things that appear in what's known as an object table. So you can retrieve these. The typical way that you would do this for Butler data products is to retrieve these as pandas data frames. So let's try that for one of these. Let's go back to, again, this is the sources measured from a specific CalExp. So again, we need the visit and detector, and we'll look at the source table for that. And if we say source equals butler.get, that source table with that data ID, we shall now have a list of, you can see 2,548 sources and all of their measurements. Here's what that looks like. It is a big table. I can't even find the scroll bar. It's a big table with, you can see 143 columns. So you can do that as a way to retrieve catalogs as an alternative to the TAP service. The analogous table for difference image is the DIA source table. So DIA, remember, is difference image analysis. In this case, all of the separate detectors from a given visit are grouped together. So for this, you don't need to specify the detector. You just specify the visit, and this will give you the DIA source table for that entire visit. And so this should correspond to the data set type that we showed you, the difference image above. And so you can see there are 11,000 difference image analysis sources, and here's what the table looks like. And you can see this has things like the midpoint of the observation and various different measurements than the typical, or than the previous source catalog that we looked at. You can, because I mentioned that the DIA source table is not broken up by detector. If you want to only pick out the detector that corresponds to the image that you have grabbed, you can do that from this information that's in the source catalog. It's basically this CCD visit ID column has, if I go back up, you can see that we specified visit 192,350. So those are the first 6 digits of that. And then the final 3 digits correspond to the detector, so to the CCD ID. And so you can see this one would be that visit, detector 0 at the end. It's that visit, detector 188. So if I wanted to pick just detector 5, I want to take that that detector number and turn it into a string. And then this line just paste together the visit number here and the detector number and padding it with zeros to make sure it has 3 digits into something of this format. And then you can just do a selection on this pandas data frame that you have, where you say, just give me the ones where that CCD visit ID column equals what we've created here. And we'll see that this has only 57 DIA sources out of those 11,000 that were in the whole visit. And here's what they look like. And hopefully we were successful, yay, in getting the CCD that we wanted. Okay, and finally, the COAD image objects detected and measured in COAD images are assembled by tracked and patch again. These are assembled all together from all of the filters that are observed. So you have in here potentially UGR, IZY band data. So we still can specify just the tracked and the patch, and we'll get back all the data from that patch, but from all of the filters. And you'll see that here so there are 37,000 objects, and somewhere here, we'll be able to see there are 990 columns, by the way. You can't actually see it, can you? So you could do a similar thing like we did on the CCD visit ID for the difference imaging. You could select, oops, isn't it banned? Oh, it's probably, no. It's filter. Is it? No, that's not correct either. When in doubt, you can print the list of columns in. Right there. The filter is just prepended at the beginning of each column. So if I wanted the PSF flux in G band, I would say G PSF flux. Flux, I think. No, maybe it's just G PSF flux. Yeah, there you go. And so each of them have the band prepended at the beginning of it. And again, to see what columns are here, you can do this .columns method. And that will bring back all 990 of those. Checking out how we're doing on time here. Okay. You can get the difference image objects, which are from all of the I guess it's the unique set from all of the difference image sources that have been detected in a given tract. And so here again, we just give it the tract, and it'll give us back the DIA objects for that entire tract. And you can see things like here's the number of DIA sources that were detected at the position of this object that had 300 detections, for example. One more thing that exists is force photometry. This is where we have the sort of master list of the object table. So we have everything that we've detected in all of the images. And then we, at each of those positions, we go back to all of the images and we say, measure whatever's here, even if it's 0. So we force it to take a measurement at that position or for every position. So this, of course, can be a really, really big table because for every object you're going and doing forced measurements on everything. So the forced source table is actually really massive. So there's a warning here. Be careful because it returns too much to work with unless you do some constraints. So we're going to skip this part where it says only do this if you're using a large container. You can explore that later if you like. But again, so this is, in this case, forced source on the difference image objects. So everywhere we've ever detected a difference image object, or sorry, every object we've detected and cataloged, we actually go back to all the images then and do a measurement at that position. And so this is for a tract and a patch. You can see it's really big and it killed my kernel. Thankfully, we're at the end of my demo, so so all's well. Because I had other things in memory in one of the other tabs that I had open here. So that's what happens if you try and load too much into memory all at once. But anyway, that's the very basics of accessing certain data products with the Butler. And then Douglas is going to show you much more detail about Butler queries. So if there are any questions, I'm happy to take those. Or else we can just roll on to the complicated stuff.
All right. I guess if there's no other questions, we can move on to the next tutorial, which is 4B. Let me share a screen here. All right, people can see. Oh, people can see the notebook.
Yes.
Great, thank you. All right, so here, before we showed how to grab data which we sort of knew about, like the visit ID or the patch track number and so on. Here, this notebook kind of goes beyond that a little bit to actually hunting down what data are available. So you can doing data discovery and querying with the Butler. Let's see. Well, okay, so a lot of this is what we have seen before. We'll use the Butler. We'll need to know the so in the let's see. So in the introductory Butler tutorial, we learned how to access the data given a specific data identifier, a data ID. But here we'll use you'll use the Butler to find available data sets and then load things up. So first of all, we will just do a standard loading the various Python packages in the stack package, and we'll also kind of just set up parameters for the figures in this first cell. And then, as we did in the previous tutorial, we will create an instance of the Butler using the DP0.2 configuration and the collection 2.2i/runs/DP0.2. Basically, what we've been doing throughout is the data set that we've been using throughout these tutorials. So we'll just do that, and then we will define a function which will come in later. It's not a major function, but it's useful for a place where we print out some information a bit later on. So we'll create this get corners aria deck, which makes use of the WCS of the image and a bounding box that we provide within that image. Okay, so the Butler repositories have both a database component and a file-like storage component. So the database component is in what's called the Butler registry. We've seen a little bit about that before. Here we'll look at it in more detail. And the file-like storage component is more or less accessing effectively like data files, but they may not be actually in data file format. They could be local files, or they could be, in the case of the interim data facility, the IDF that we're using here on data.lsst cloud, we're using something called the simple storage service, or S3 buckets, which are in the cloud, and they're similar to file folders, and they store objects. If that confuses you, that's all right. It confuses me. I just accept it. It's but I kind of view them sort of like files. They're file-like objects, and you don't need to worry about that. Butler, and another thing is the Butler, whereas before, actually in the earlier version of the Butler, where you kind of had to know where data were, you can use the Butler here to access them without knowing where they are on a file system or where they are in this S3 bucket system. It helps you find it. So let's see, the Butler registry. Okay, so the database, so that's like the various metadata for concerning the images and so on, basically it's more or less in a database. So we will create a registry here. We will due to time, we won't go in depth, and we'll leave this for the interested user to look at the help section. Okay, here we're going to use a method of querying the collections. So we have a method aside from the tap server to actually query the data, and here we're kind of focused on querying data which is associated with images, leaving catalog data querying pretty much that's better done with the tap server. So just to remind people, collections are lightweight groups of data sets within a repo, like the DP0.2 repo. And we're looking at a collection the collection that we're interested in typically is 2.2i/runs/DP0.2. And that we specify that when we create our instance of the Butler earlier on. We can also query other collections that may be available, or might be on in the S3 storage area of this cloud data set. But we also like to remind people here for the interim data facility, which uses the Google Cloud. We don't have any read-write restrictions on the Butler repository. So this means currently all users can see everything in the Butler, including intermediate data processing steps, test runs, and so on. Later on, we'll probably plan is to kind of tighten that up. So when we do releases and so on, you're not inundated by all this extra information. I will kind of skip over this one because this is a very long list of all the many collections. But you'd also just pull out the ones which may be of interest. So the DP0 delegates have been in the past, we're using DP0.1, the data processing 0.1 collection. Now they're using the DP0.2 collection. And you can just you query the collections and just print out the ones which have something to do with that. And so, yeah, we see, okay, yes, they're in there. You can also use regular expressions to basically search for various things. So, here, here we can just create the collections which were created that are in Melissa's user space, and so we can see which one. We can see what she's been up to. So so there's various collections that she has created. Mostly, it looks like about a year ago in June 2006. So it looks like they have the timestamp on there. You can also, for instance, see what I've been up to. I've not been up to very much. Maybe I should. I think I might not have created. Oh wait. Oh yeah. It's all lowercase. Okay, so I've actually done something, as opposed to what some people may say. So I did. These were actually from a few days ago when I was preparing something, practicing something earlier on. Okay, so okay, let's. In addition to creating collections, we can also query data set types. So as mentioned before, previously we know that the Butler contains data set types for images that include deep coad, calyx, XP, good scene, difference exp, whereas things which are sort of associated with catalogs include source table, object table, DIA object table tract, etc. So we can query those too. We do note, however, that using a registry query dataset types will report all the dataset types that have been registered with a data repo, even if there aren't any datasets of that type actually in the repo. So that is one caveat. But it's also a useful function when you know the name of the dataset type already. You just want to see how it's defined and see, for instance, see what data ID accepts. I will skip this step. We'll see sort of a variation of this in which we can actually use a regular expression to see all the query set dataset types that have underscore tract in their name. Otherwise, it's this first one, because it's a very long table, but we just look at a shorter table. And so here we find all the various data set types that have tract in their name. So and you can also do it with other things like well, we could also even just do it for this other one, which everything has coad in their name. All the data set types have coad in their names. And so there's a bit more here. So you have things like the coad Kali XP, background, exposure time maps, weighted mean maps, the sky background, noise maps, and so on. Let's see, where are we? We do know the query data set types return the generator function, which can be iterated over. It contains objects that can be looped over like a list, as we just saw. Generator functions are kind of useful because they do not store their contents in memory, which makes them useful for kind of querying through large data sets like we have with Rubin. If however you know the name of the data set that you care about, you can use instead of query data set types, you can do get data set type. So for instance, we can get the information for deep coad here, and we find, okay, it's a data set type is the name is deep coad. It accepts band, sky map, tracked and patch in its ID, although of course tracked and patch are all you really need. And it's a exposure F object, which means it has pixel information as a plane, as the basically the image information. It has a mask plane. It has a variance map plane. And we can see these things. I think we go into that a little bit more detail later. Actually, I'll stop briefly here to see if there are any questions. And I should actually look at see the chat, if there's anything in the chat. It does look like it. All right, let's continue on. So okay, you've seen before that the Butler data ID is basically like a Python. It's basically a Python dictionary like identifier, although that you can feed it as a data type, but when it's returned, it's actually returned as a data set type. So we use the registry to get the data set type for names data set like CalXP and list its dimensions. So we can do that here, and so you see the dimensions as contains band, instrument, detector, physical filter, visit system, and visit. And of course, when we're querying things, we really only care. I mean, you can just define it as a visit and a detector. These other things are sort of extra. And it notes that it's again, it's one of these exposure F objects, which contains the image, the image, the weight map, basically a variance map, and a mask plane. And so that's here, and we don't hear that, as I mentioned, the data ID contains both implied and required keys. And for instance, band is implied for CalXP, band is implied by visit, because you're taking one exposure, you only have one band per exposure. Let's see, other tutorial notebooks we've seen how to access the specific data product using a specified data ID. Query for a fully specified data ID should return one unique entry, but there are some caveats associated with that, associated with chain collections, which we'll leave for the interested person to explore on the FAQ page. So let's take a look at a particular visit and detector for a CalXP, and we will query it for the data set type of CalXP and for that data ID, and we'll kind of go through the data set refs, and we'll run that. Okay, so we find out here, okay, the instrument is LCD cam IMSIM. It's just the simulations. There's no other instrument that we have for DP0 use. The band, the detector, the physical detector is based upon the simulated I-band version 1.4 that went into the simulations. And because the visit, I don't quite recall what visit system is about. Does anyone else recall? No. In that case, ignore it. Well, no, not really. One can look up and see what the details are. These details are. We'll ignore it for the moment. Okay, let's see. Moving on. Let's see. What is different from that? Oh, yeah. Here we just give the visit, and so we'll get a whole bunch. We'll get several things returned. Several data set refs returned. Actually, one for each of 187 detectors. Actually, the LSST science camera has 189 science detectors, but this particular visit was very near the edge, the simulations. So the two of the detectors got chopped off. So there's only 187 in this one visit. And let's see, was there a mention of set here? I don't see that. Do we use that? I'm not seeing offhand. There was a mention in here. You can use the set command to get rid of it's set command in the previous cell. Where is that? I'm not sure if I
It's
see
actually
that.
right below.
Right below?
Right below the found 187 detectors. There you go. The use of the set method.
Yeah, but I don't see it being used up here. But, okay. But anyway, that using the set command kind of removes gives you a unique set of things. I think we do use it further down though. Okay. Moving on. One of the nice things about the butlers, you don't need to know exactly where the data live in order to access them. So before we use passive data ID to butler.get to return an instance of the appropriate object. But if you already have the data set ref, it's actually faster and more efficient to use butler.get direct as opposed to butler.get. And here you use butler.get direct using the data set refs from above to retrieve the CalXP file, CalXP and the detector ID. So we run that. And here, and we'll just stop after three objects are output. So yeah, you get some information there more quickly using oh, here was get. We didn't use the get direct here. That was
yeah, I realized that yesterday, Douglas. That recently changed, and the code cell got updated, but the documentation part didn't. So I have a ticket that I didn't get a chance to merge yet to fix that. So it is actually butler.get now.
It's just butler.get now. Okay.
Yeah.
All right.
Get direct still works, but it'll just give you this warning that it's gonna be deprecated.
Things change. All right. Okay. All right. Thanks, Jeff. Okay. Okay. Just for grins, we can actually see so we can look at the images of these first 4 CalXPs that were returned. And so let's take a second. All right, so there's the first one, the second one, third one, and fourth one. Okay, any questions at this point? We're going to move into a slightly different territory now. All right, let's continue on. We'll query the DP0 data repository. So as once again, we should note that the tap service is recommended to query the catalogs, but we're gonna query basic temporal and spatial. We'll show some basic temporal and spatial query examples for images in this case for the CalXPs. So first of all, we can use basic image queries. So what we did above was a simple use of query data sets, but additional query terms can be used such as ban and visit. And I can use for instance, we can set band. We can set band equals to a value, or use a where clause, sort of like in SQL. So here we'll query for CalXP data type IBAN detector 175, and we'll query for all visits between 192,000 and 193,000. and then we'll just print out their data ID info. And so it goes very quickly. And you see, yeah, visit 0, 50, 51, 52, 54, 55. They're all basic sequential, this set. You can also grab the data set refs, but we'll just skip that for now because we're kind of running out of time. Okay, we can also retrieve time and spatial metadata. So here let's print the full visit info record to the screen from the data set refs that we defined using this query. So we can do that. And it's kind of messy. It's a lot of stuff in there. But we can also clean that up and just grab particular information. So I amended this slightly just to show the visit ID number also. The originally shows the date, your time, and Bohr site ARIA deck. I thought also adding in the visit ID was useful, so I commented out the original line and added this. So here we have, once again, 50, 51, 53, 54, 55, 56, 57, 58. 52 is missing. I guess it was missing from above. I didn't notice that. I get the date in UT, the exposure time, and the ARIA deck of the Bohr site. And we can also print spatial information. We can get the bounding box for at the WCS for each of these data IDs, and print out those information. So here again, the bounding box in ARIA and DEC. And here's where you use that function that we defined at the very beginning of this get corners ARIA and DEC that we define at the beginning of just after the imports at the beginning of this tutorial. Let's see. Let's say in case our metadata is designed for many images at once, you can avoid the time-consuming use of the Butler get for individual IDs by retrieving the expanded data set refs, which we do here. And this goes quickly, and then you can just print things out, and you basically print out the same sort of information as before. Okay, moving on, we can also look at we can also do time-based queries. And say you're interested in all Kali XP visits or exposures within a plus or minus 10-minute time frame of a given visit. So first of all, let's define the data ID for a given Kali XP. So a good visit number and a detector, and we'll grab the visit info from the Butler for that data ID, and you get the information about the R, that same set of information, which also includes the UT time, the universal time of the observation. Now, formatting this for use with the Butler, creating the Butler is kind of messy. And if you're going to do like plus or minus 10 minutes, it's a little messy, but you can use something called the bind command, where you can pass time arguments to the where clause and do relative time queries. And you can that's what we'll do here. We create a timestamp based upon the visit information from up here, then we'll create using action file, we'll create a minute of time object, and then we'll define a time span based upon minus or plus 10 minutes from that visit, which you do here. So you get running from 8:57 UT to 9:17 UT. So we developed a time span that we want to query, and then you can use the registry to get the data set refs for this CalXP. And we want the visit time span to overlap my time span, where my time span is defined by this time span up here, this plus or minus 10 minutes. So you can run that. It runs very quickly, and then you can see some of the things that were returned from that set. So we actually have over 1,600 CalXPs, but here this includes also the detectors. So there's 189 detectors per visit, except when you're on the edge, and you have fewer. But you want to kind of wonder how many unique visits were obtained within that plus or minus time frame. And here's where you use that. And here you can use the NumPy unique command. And so we basically loop over the dataset refs, grab the visits, and append them into a temporary array, and then a NumPy array, and then just find out how many unique visits there are, and output the names. And we do that, and there's 13 unique sets. We do note that with the cadence, it's basically 30 seconds per visit, and there's a very quick slew time. We usually expect on average to do about 34 visits in a 20-minute time frame. But the reason why we find only 18 is because the observing strategy that we use here assumes that you're covering the full sky. But DC2 only covers 300 square degrees, so it's a subset of so there's things which are the observing strategy assumes visits outside the DC2 or DP0.2 footprint, so those are not included in DP0.2. Let's see, moving on. Yeah, we're a little bit over time, but we can kind of relatively quickly go over this. So spatial image queries, say you want to say, I want to look at all the CalXPs in this part of the sky, or in this case, we look for deep coed images that overlap a particular CalXP. We grab the visit information for that particular CalXP again. And we can query for we can just print everything that let's see, use if we query the deep coed data sets with visit plus detector, let's get the coed objects that overlap that observation at the same band. And this is very similar. We just do that, just print out the references here. So we have so we're grabbing all the references that have that data ID in it. Now we can also use the corners of the CalXP and the overlapping deep coed patches to trace the image of the edges in a plot and show the overlap. And we'll do this using the WCS and the bounding box for the CalXP. And grab it from the butler and define the corners. And once again, we use that function that we created, was created at the top of this notebook, and then we can print that out. Or I mean, we can not print out, but we can show the image. I'll take a few seconds here, and so here's the detector for the Kali XP, and these other things are the deep coads that are in or near, that overlap or nearly overlap the visit detector. Any questions at this point? All right. Now we can look at user-defined spatial constraints on images. Now, right now, arbitrary spatial queries are not supported because basically it'll only return things. It only will return things if they're already in it. They know it's in the database. It doesn't understand about what's outside the database or what's not covered. So it knows what is covered. So you can query things by their tracked, patch, visited plus detector, or we can use something called the hierarchical triangular mesh, or HTML pixel regions to query spatially. We won't go into too much detail about the HTML pixelization, but basically it's many different levels of. You'd have bigger triangular triangular meshes, which are within which are smaller ones and smaller ones and smaller ones, and you can choose the level to choose the fineness of how well the sky is basically sharded up. But we don't need to worry about that too much. We'll just kind of follow along here. We'll use the LSST spherical geometry package, and we'll initialize, and we'll look at a HTML pixelization level of level 10, which is what is it? Oh, it's in which one sky pixel is being about 5 arc minutes radius. So it's fairly reasonable for what we're looking at here on for patches versus visits. And then we'll find the HTML ID for the desired sky currents. And you could give your own user specified currents, but here we just want to grab the Bohr site for this particular Kali XP info. So we grab the R-index from the Bohr site information for this particular thing. You could have just put something random that this lies somewhere within the DP0.2 footprint, but anyway, we'll create a HTML ID. We'll find out what the HTML ID is for that R-index. This nice code that will calculate for us for at a level for at this level 10 of pixel of resolution. And we're kind of curious what the size of the pixelization is. We can kind of get a rough idea looking at what the bounding circle is using this cell. So it's about 280 arc seconds radius circle. So it's not huge. It's not huge, or it's not small. And then from what we're looking at before, we want to do a time. We also want to select on time. We'll just select plus or minus 1 minute around this visit, this Kali XP visit. So we'll use a small time span here, and then we can query the data sets, the Kali XP, use it, and we for this HTML ID, like before, we use the where clause to find the time span that overlaps the time span that we're interested in. In this case, it's not plus or minus 10 minutes here, it's plus or minus 1 minute. And then we can just print out ones that print out what we have. And in this case, we found one exposure, and that's partly because we use just a pretty small, relatively small spatial query of these HTMID. So you can make it. You can, however, use a smaller HTML level, which will give a larger sky pixel. In this case, about 2/3 of a degree, and that'll return many more visits. And actually, I'll leave that for we can leave that for if you're interested. One can go and try that oneself. We do note that level 7 HTMIDs that overlap each visit are already loaded into the registry, and so we can access those directly. Those are actually already previously saved, and we can access those using the query data IDs. And so we can do that here, where we're using where we query the HTML7 IDs for ID for that visit. It's actually there's two ends up being, it overlaps two HTML7 pixels, and we can, and then afterwards we say, oh, let's look at that one HTML pixel in that HTML7 value, and once again we can query. And actually, as mentioned before, the level 7 covers a larger area, so you end up having a lot more Kali. We found this time we find 22 Kali XPs that overlap with HTML7 of 147.116, the HTML value of that sky pixel. All right, and then finally, we can do catalog. Here we're querying for images. We can also do catalog queries, although once again we generally reserve catalog. We generally recommend using the TAP service to do catalog level queries. We can also query on, say, the source table in this case. So here we're querying at the HTM20 level for things that actually I'm a little confused here. Oh yeah, we didn't redefine HTMID. We create HTMID up here. Up here where we pixelated things on resolution 10, level 10. So we basically just query the source table here, and we find 2,290 sources here, and we can take a look at those sources, and RA index, and so on. All right, and that's it. Sorry, I went a bit over. Are there any questions? All right. Well, in that case, I will stop sharing screen. Oh, thank you.
Thanks, Douglas. That was a lot to absorb, so we probably all need a few-minute break. So we could take a few-minute break, and we can come back. And as we have been doing, we can form into breakouts of your choosing. So if there's something you have an idea that you'd like to work on, let me know, and we'll make a breakout room for you. So let's take, should we do 5 minutes? So we'll come back at 17 after the hour. Let's see you all soon.